let's jump right in. I would like to give you a short intro to my work on carbon management within transformation pathways. And I would like to start doing that with a short introduction by giving you a bit of context. What are the scenarios we're working with? How does the integrated assessment model work? And then I would move on to some of the current interesting research questions we are looking at and some exemplary results. And then in the end, have a bit of an outlook on what we're currently working on and what current and future research questions and projects are. So I will be talking a lot about scenarios here. And what I mean by scenarios is not a description of possible actions or events in the future. So more specifically here, it's a description of the energy, land, economic, climate system in the 21st century. And what's important here is that it's really a description of possible events. It's not prediction of the most likely event. So what we're trying to do here is we're trying to have explorative scenarios. So we don't have the most probable scenario, but we try to span a range of possible futures given different assumptions. And in order to generate these scenarios, we are using integrated assessment models. So integrated assessment models are comprehensive and consistent descriptions of the energy system, the land system, economic and climate system. And they usually give us things like energy use, land use, emissions, investments, developments of technologies and prices, and so on. But they also rely on quite a bit of assumptions. For example, socioeconomic drivers. How does the world population develop? How does the labor force develop? How does the world economy develop? But also technology. So what kinds of technologies do we have? How costly are they? So if you think, for example, what happened in the last 10 years with renewables, prices dropped quite dramatically. And that was something the models obviously had to take into account. But that's also what we need scenarios for, because 10, 20 years ago, we couldn't know how fast prices would drop and to what level. Of course, we have an idea how fast usually prices of new technologies drop, but we use scenarios to sort of span the range. And then a third sort of type of assumptions we have is policies. And that's not only climate policies, but also energy or air pollution policies, for example. Now, that's quite a large range of assumptions. If you think of technologies, you would need for all the different technologies like coal power plants, solar systems, heat pumps, you need to know what are the investment costs, how do they develop, what are resources for coal, oil, gas, how do these prices develop, how does the population develop, so how does our energy demand develop. So there is a range of assumptions we have, and since there are so many, we can't just vary every single one of them and check what the impact is to give some sort of range of uncertainty. But what we do instead is we developed different narratives that vary a range of assumptions at once. And that's what the so-called shared socioeconomic pathways did, the SSPs, in case you may have heard of them. They tried to develop different narratives that are very different, so they span the scenario space, but they vary a number of assumptions at once, but in a way that it gives a plausible future. And then we also, of course, vary things like the climate policies, and that's what the RCPs did, the representative concentration pathways. So we not only look at 1.5 degree scenarios, but also 2-degree scenarios, or at what would happen if you just continue current policies. So that's sort of the general framework we're using. I have 2 more slides on a bit more detail of the modeling. I will just go over them now. I just leave them in here for reference. So you have them because I assume I will be distributing the slides. But what I would do now is I would rather, oh, sorry, lots of, we don't need that. I would rather come to some examples of our output and then jump into the research questions. But maybe one word here, because that was now very general on integrated assessment modeling, but I would like to talk specifically about carbon dioxide removal. I'm not sure to what extent I have to give context here, but maybe let me just say one word on that slide here. So that's sort of one of the prime examples for outputs that we get from these models, and that's global greenhouse gas emissions trajectories for different climate policies. And here you see how a typical emission trajectory looks like. And for 1.5 degrees, we have to have a peak of emissions now, followed by a fast emission reduction. And then all of these 1.5 consistent scenarios achieve net neutrality and then also net removals in the second half of the century. And that's the prime reason why we need carbon dioxide removal. It's wants to offset residual emissions to really achieve emission neutrality and to be able to halt climate change. And so we really needed to achieve our climate targets. And then we could also, on top of that, if we temporarily overshoot the temperature limit of 1.5 degree, we could also use net removals to reduce global mean temperature and get back to the limit. So carbon removal is an integral part of these ambitious climate scenarios, even though it's not the most important. Obviously, emission reductions is the most important, but it's an integral part, and we don't have scenarios anymore that can do without. And that's one of the reasons why we're interested in carbon removal specifically. But even though many people agree that we do need carbon removal to achieve the targets, there's still quite some disagreement as to how much we need. And that's one of the first research questions we tackled here, followed by sort of the related questions: what are the most important drivers of CDR demand? Because as you can guess, there is not one single number at the answer as to how much we need, but it of course, again, depends on assumptions. And then we also looked a bit deeper into the different CDR options. So what effect do different options have, and also additional options in portfolios? And where could be synergies and trade-offs between different options? And then last, once we've answered these questions, we would like to know, how can sustainable and low-risk CDR pathways and portfolios look like? So let's start with the first one: how much do we need? And what we did here is we used our integrated assessment model Remind, and we started with a 2-degree target. And we started until 2030 by following the NDCs, the nationally determined contributions. And what you see here is that we need quite a large amount of carbon removal, depending on how fast we can reduce emissions after 2030. And to give you a bit of context here, not many people know much about these average emission reduction rates. If you have an average reduction rate of 7%, that means halving emissions every decade. So that's quite ambitious. What we've seen in the past is something like 2 to 3% for some countries for maybe a decade. So that's, for example, what happened in France when they moved towards nuclear power. They were able to reduce their emissions by 2 to 3% annually. So here we're really talking about different worlds. And when I wrote that paper and I showed it to policymakers, they would run away screaming if you mention anything above 5%. And we're talking here global, sustained for several decades. So that already shows us following the NDCs is not an option. We would need huge amounts of CDR in combination with very large emission reduction rates globally for 20 years, between 2030 and 2050. But we can alleviate these trade-offs if we do more ambitious near-term climate action. So if we would end up at not the emissions that the NDCs promised, but by only half of that, which is again, of course, very ambitious. But as I said, these scenarios are about spanning the space. The truth will be somewhere in between. If we would manage to halve NDC emissions, then we would end up at this red line, and that looks much better. Then we would actually have a chance for sort of more reasonable CO2 reduction rates in combination with more moderate CDR. But you can also see no CDR, even for a 2-degree, and that's like a 5-year-old publication, right? In the meantime, we haven't really moved toward that red line. So no CDR, even back then, was not really an option. So that already shows that's rather theoretical, and we need carbon removal, even for 2-degree pathways. And then just to show you one example of of some variations following these SSPs I mentioned in the beginning. We did the same study with different SSPs, SSP 1 and 5, and we actually found that it's quite robust, even though these narratives are very different. So even if we end up in very different rows, this correlation sort of holds. But that was for 2 degrees, and we repeated the same exercise for 1.5 degrees, and we found we need much more carbon removal. So that already answers sort of partially the second questions, what's the driver for CDR demand? And we see that our CDR requirements are already substantial, and they even increase if we delay our climate policy further. So if we do not substantially enhance or increase the NDCs. It increases if we have a rather slow transformation speed after 2030 still. And of course, if we have increased climate ambition, then we also increase our reliance on carbon removal. So that was the first research question. We partially answered already the second one. And maybe let me mention here, we did sort of a national bottom-up study for the carbon removal requirements only for Germany and without the Remind model. And I'll just post the link here. Unfortunately, this is in German. It's not yet available in English. So I'm not sure. Maybe some people could be interested in that. So I will just leave the links here on the slides for later. So now, actually, we should have answered the second question, right? What are the most important drivers? It's delay, and it's more ambitious climate targets. And we've shown here that for 2-degree pathways, it should be something, I mean, most models usually assume rather immediate ambitious climate policies, so they should be somewhere below 5 gigatons, right? That's what you would expect after seeing that slide. But if we look to the database of the special report on 1.5 degrees, we see that there's actually quite a large range of carbon removal and that it's way above that. So all these thin gray lines are single scenarios in the database and the thicker red line is the mean. And you can see also for the net CO2 emissions, we have quite a number of scenarios that go very deep into net negative emissions, even for 2-degree scenarios already. So since they all most likely assume, or if you look at the emission trajectories, most of them assume rather immediate policy, there must be another driver of the CDR demand. And we found that when we looked at the carbon price. Again, these are the carbon prices of all the single scenarios, and the red line is the median. And what you see here is that most scenarios use exponentially increasing carbon price trajectories. And if they increase exponentially, that means that towards the end of the century, you can reach very high carbon prices. You can see here the scale goes up to $5,000 per ton of CO2. And even there, I'm cutting off some of the scenarios. So they end up at very high prices, which leads to high CDR deployment and high net negative emissions. So that's an exceed and return to the temperature target, even though for 2 degrees, the target should never be exceeded. So there's no need for returning and for no net negative emissions. So that tells us that these exponential pathways are actually not suitable for, at least not for 2-degree scenarios, and maybe not even for 1.5-degree scenarios. So we need a different structure of the price pathway for stabilization of the temperature. And maybe I'll go a bit faster over that because it's a bit more technical, but what we did is we experimented with different pathways and we found that sort of an optimal stabilization pathway is one that follows that exponential trajectory, but only until the point of net zero emissions, and then it stabilizes. And that leads to a rather high early price. So we have fast emission reductions early on, but then we have moderate or no growth after the carbon neutrality, and that avoids excessive carbon removal. And here you can see that, sorry, that's the amount of carbon removal we saw in our scenarios with these different price pathways. These brownish scenarios here with a very high carbon removal of 20 gigatons exponential price pathways, and the optimal pathway with the stabilization is here, the blue one, where we could just more than halve the amount of CDR that is necessary. And that also reduces here the amount of net negative emissions. A third question we had is, what effects do additional CDR options have? So far we just looked into carbon removal in general. And most of the models and scenarios use only a very limited number of carbon removal options. So they tend to have bioenergy in combination with carbon capture and storage, so BECCS. And some of them also have afforestation and reforestation, but most models don't have more than that. But there's a lot more that being discussed, as you see here. There's soil carbon sequestration, biochar, direct air capture, enhanced weathering, some ocean options. And so we were interested to see what happens if we add more options to the model. And that's what we did. We added direct air capture and enhanced weathering in the first step. And one of the problems was that for direct air capture, that's a rather new technology, but there are some numbers around in terms of costs and energy requirements. But enhanced weathering was so new to the debate that we didn't really find any literature, and we had to derive the parameterization ourselves. But that's what we did, and we added those options, and we looked at the effects. And so we just ran different scenarios where we had only one of these options available. So that's the colored scenarios, and one scenario where we had all of the options available. And you see here the CO2 trajectories in the 21st century, and they're rather similar. I mean, they're not the same, but they look rather similar. But if you look more closely, the carbon removal is very different. So the potential of these options is very different. Some of them, like enhanced weathering, just can't do much more than 3, 4, 5 gigatons per year, while others like BECCS have, at least in theory, a higher potential. It's widely debated, but here we're just looking at economic drivers. And we didn't constrain based on many environmental impacts. So that's probably also more on the high end. And maybe one interesting result already is that if we have all of the options available, then we increase total CDR, but it's not like the sum of all of them. So there is some competition between some of the options, which makes sense because afforestation and BECCS, for example, they both compete for land. You can only use the same amount of land to either grow food crops or to grow bioenergy crops or to afforest. So there's competition for land here. BECCS and DACs compete for geological storage space. So it's more than, it's quite conceivable that the full portfolio cannot be the sum of all of them. Unfortunately, you don't see the tier. What's interesting is that the composition changes. So if you have a portfolio of options, you have more CDR in total, but you're using less of each of the single options. And since many of the negative side effects increase with deployment, so think of BECCS, for example, the more bioenergy we need, the more severe would be the consequences in terms of pressure on land, water use, maybe also biodiversity, depending on how you generate the bioenergy. So by using the portfolio, even though you increase the amount of carbon removal, you could potentially reduce the environmental side effects. So that's already one important result here. Another important issue is when we look not only at the global deployment, but also at the regional deployment in 2050. So here we have the regional CDR deployment for 4 exemplary regions: Asia, Latin America, OECD, and Middle East and North Africa. And I show you here the CDR deployment in 2050 for these different scenarios, the full portfolio and for the single options. And if we now focus on the scenarios where we have only afforestation and reforestation, that's the AR, or where we have only enhanced weathering, then we see a very strong regional imbalance. The main potential here is in Asia and in Latin America. And that's one of the problems when the CDR portfolio sort of relies only on land-based options like afforestation and reforestation. That means that since the most potential is in the global south, that the global north, like OECD, for example, they wouldn't do much CDR. So all of the responsibility for CDR would be shifted to regions like Asia and Latin America. These letters that you see here, they are different different indicators for responsibility, capability, and equality. So for what could be different types of fair distributions of CDR. And you can see that here for these, for afforestation, reforestation, and enhanced weathering, Asia and Latin America would by far exceed their fair share, and OECD would not meet it by far. In contrast, if we look at direct air capture, DACs, that's the one to the left, we see a bit more of a balanced contribution. Still, OECD doesn't achieve their fair share, but at least they come a bit closer, and Asia and Latin America are also a bit closer to their fair shares. And same holds for the portfolio. So that's another argument for not relying on a small set of carbon removal options, but for developing a broad portfolio of options, because that can balance the regional deployment.
Jessica?
Yes.
May I ask a question? This graph is really interesting. Can you explain what is the blue bar compared to the letters? I think I understand the letters, but not exactly the blue bar in relation to them.
Sorry, yeah, thanks for asking. I didn't mention that it's the blue bar. The blue bar is the CDR deployment that we get out of our scenarios. And the letters are just calculated fair shares based on the total CDR in that scenario. So if you, so the blue bar indicates how the model distributes CDR across the regions, and the letters indicate how a fair share distribution should look like, given the responsibility principle or the capability or the equality principle.
Oh, okay. So in the case of the C letter being below the blue bar, that means that there could be more opportunities for that particular CDR technology, but the capability is limited, and the other way around. Am I getting it right?
It's not the capital. It's the distribution, a fair share distribution based on capability. So that means based on economic affluence. So the richer countries would have to do more than the poorer countries. And equality means all countries do the same per capita amount of CDR.
Okay, thank you.
Is based on historic emissions. Yeah, thanks. Yeah, I continue. I'm actually almost at the end already. So the final research question that's left is, how can sustainable low-risk CDR pathways and portfolios look like? And that's actually a question we are currently looking at in some of the projects we're working on. So there's, for example, CDR Sintra, which is a German project that's part of a larger research mission called CDR Terra. And here we are looking to first expand the CDR portfolio further, because you've seen we don't rely on only 2 options anymore. We have 4, but still there are very important options like biochar, like soil carbon sequestration, and we are aiming to expand our portfolio more here. We're also working on including one ocean option. So OAE, oh sorry, I didn't write that out here. OAE is ocean alkalinity enhancement. So we're also trying to look into the parameterization of ocean alkalinity enhancement. And the aim of that project is to have a comparison of a very broad portfolio of CDR measures, going beyond the 4 that I just showed, by including biochar, carbon fibers, and potentially also oceans. And here we have a collaboration with social scientists, natural scientists, and earth system modelers. And here we actually aim to also constrain all of these options based on environmental sustainability, political economy, social impacts, maybe also geophysical impacts, if that works out. And the goal is then to derive low-risk pathways for Germany and the EU. And a second project that will start this summer is Uptake. That's an EU Horizon 2020 project. And here we are together with some other integrated assessment modeling teams. And we aim for an improvement of all of these integrated assessment models, including a bottom-up assessment of a broad portfolio of measures. Besides these things, we are exploring sort of a range of research questions, and maybe that can be part of our discussions as well. So we're interested in general in CDR and transformation pathways, in synergies, trade-offs, interactions between the different CDR options. I've mentioned some of them, like BECCS and DACCS compete for storage, afforestation and BECCS compete for land, but also for these trade-offs, interactions between CDR and mitigation options. Constraints are an important topic that we're looking at in the CDR Sintra project now, biophysical constraints, but also ecological, institutional, governance, whatever, because there's been lots of criticism around, and I share some of that at least, that the CDR demands in some of the scenarios, or in many of the scenarios maybe, have been overestimated. And we're looking at how can we constrain it, but also what happens when you constrain carbon removal, because then of course you have to do more emission reduction, and that leads to much higher costs, and that also can have negative effects. So we're looking into comparing those. Sustainability and distribution justice effects is another important topic, and also one expanding more the portfolio. So materials like carbon fibers is an option. The potential of wood as a building material is also something we would like to explore a bit more. So all this about materials and expanding the portfolio is also of interest. So with that, I'm at the end. Let me just briefly summarize the last 25 minutes, I think it was. So I started out by explaining a bit about what scenarios are, and for us, they are not, we're not trying to predict the future or to look at the most probable outcome, but for us, they are if-then analysis, and we're trying to explore a broad space of, or a broad range of possible futures. And for that, integrated assessment models are useful tools to analyze different mitigation options, and most importantly, taking into account the system perspective. We've seen that carbon dioxide removal is necessary to achieve the Paris climate target, and that our reliance, though, can still be reduced by immediate ambitious mitigation action and by fast transformation. One other important point was that we should not rely on one or two options, but it's important to develop a broad portfolio of options, because that can reduce risks and also balance the regional deployment. So with this, I'm at the end. Thank you very much for your attention, and I'm looking forward to the discussion.
Thank you very